First of all, I thank my acquaintance Omkar for giving me this opportunity. Now I understand that most of the participants are freshers, college students, youngsters. So I tried to make my presentation in that fashion and to give a brief introduction to chemical process engineering. Now I will share my presentation 1 minute. Please let me know if you can see the presentation. Hello, can everybody see my presentation?
Yes, sir.
Yes, sir. Yes, sir. This is visible.
Okay. Then I'll start. First of all, a heartfelt welcome to all my fellow engineers. This webinar is a brief introduction to chemical process engineering in the chemical process industry, commonly called CPI. My introduction I'll give here. I'm a chemical engineer with a master's degree. Also, I'm a PMP, project management professional, and a TUE SUIT certified functional safety professional, technical safety, what is called nowadays. 35 years plus experience I have, as Omkar mentioned in the start. I had the good fortune of tutoring, mentoring many process engineers. And with the grace of God, I am author of MIHIR's Handbook of Chemical Process Engineering, available at this website listed. And I had the opportunity of working in many premium consultancy firms in the design aspect. Now, today's webinar, I have tried to focus on a brief introduction, basically, to what is chemical process engineering. It is a very vast field, and one cannot cover it in a few short webinar. So overall, I'll try to give you an overall perspective of what is process engineering and what things are involved, how the systems are, etc. We'll cover a few equipment also. Pumps, compressors we'll try to cover, and heat exchangers very briefly. And utilities, there are many utilities. I'll try to cover this also. And then finally, what are the documentation produced? This is a very important topic in design engineering. So first we'll start with the introduction. So back to basics. The participant should be familiar with what is a chemical process plant and familiarity with chemical engineering. Learning objectives in this webinar are going to be, as I mentioned, all of these things will be the learning. We'll start with the process engineer. Now, process engineering focuses on the design, operation, control, and optimization of chemical, physical, and biological processes. Process engineering encompasses a vast range of industries. So there are many industries, chemical, refinery, petrochemical, agricultural, pharma industries, biotechnological industries. Now, process engineer most likely is a chemical engineer. Their role normally is multifaceted, and they are very much relied upon for success of any project undertaking. Now, just please understand, a chemical engineer basically, let's say, produces is helping in production of certain chemicals, let's say. So these chemicals are made in production plants, factories. So always there is, first of all, going to be a project cycle. So in that project cycle, the engineering is done so that the factory then can be erected, and then after that comes the running of the factory, which is commissioning and then operations, basically. So that is why always the design aspect is there and then the operations is there. Now, accordingly, I have listed here, process engineers are found in operating production companies, supplier or vendor firms, which are normally called OEM, which is called original equipment supplier, manufacturer. And then you have engineering consulting firms. There are many consulting firms. All of them, some of them are oil and gas upstream, some of them are offshore specialties, some of them are refinery specialties, some specialize in exact chemicals. You can have licensors are there. You can have actual chemical consultancies are there who do detail engineering. So many types of firms are there. Process engineers can also be in business development or design engineering or plant operations field. Okay. Now, process engineering emphasis. So process engineers and operational production companies need to be fully conversant with the process technology in that plant Additionally, they also need to be well versed in equipment use and process control employed if they need to carry out any modification. So this is very important. Normally the operating companies have a technical services group which basically does the revamp sort of jobs inside that production company. Addition of, let's say, one pump, maybe some compressor has to be changed, capacity has to be increased. So this is done by the technical services department. A lot of times when a project is done, these engineers form a part of a project management team, what is called PMT, of the operational company supervising the engineers of the engineering company. So that is a PMT team is formed, project management task force, project management team is formed for the operational company. Now process engineers in engineering consultancy companies also need to be conversant with process technology used in that project as well as the equipment used. They need to fully understand what is required in process documentation from them for entire team to successfully carry out the project. So BDEP, feed, detail engineering documentation. I will explain all these as we go along. Don't worry about it too much now. And there are differences in each of these stages of a project, which I'll explain as we go along. Now, process engineers in original equipment manufacturer firms will be expert in their particular equipment. Let's say a boiler manufacturer is there. So definitely they'll be expert in that boiler manufacturing. However, they also need to be knowledgeable in the design documentation produced by the OEM, which will be used by the engineering firm for their further engineering. So that is why the process engineer has to be well versed in all these things, which is my focus today, basically. Now again, I'll start with the continuation of the emphasis. Now this is important. Note that each and every chemical is manufactured by a different process technology. So for example, ammonia and methanol are manufactured by different process technologies. However, in both the processes, the equipments and process control used will be quite similar. For example, you will have pumps, compressors, reactors, storage tanks, bullets, fire heaters, distillation column, many utility packages will be there. Then you will have process control types will be there. So that is why I always emphasize that the process engineer should be well versed, knowledgeable in equipment design, utility design, and the documentation produced in the project basically. So that is why my book is also featured around that concept basically, so that in each and every equipment utility, the knowledge should be gained by the chemical engineer, process engineer, which will be helpful to him in any field basically. Okay, now types of process plants. Now you see I have elaborated here definition of plant processes. So there are many types of process plants. For example, you have continuous plant, refinery, which runs 24/7. And then you have a batch plant. For example, a pharma plant is there, or you have a small scale industry plant. So the process engineer has to think a little bit differently in these plants. You cannot have one cap fits all size. For example, in a pharma plant, as you see here, this is the batch reactor. Okay, it's a SS reactor, as you can see, stainless steel reactor, because it's a pharma plant. Small scale industry also will have like these reactors. Pesticide plants also have batch reactors. So in these, the additives have to be dosed one by one. Okay. So this sequence has to be taken into account in the engineering by the process engineer. So that let's say the control system. So chemical A, B, C, D are going to be dosed. So chemical dose, A is dosed first, B follows, then C is dosed. So this is all has to be defined by the process engineer. Whereas in a continuous plant, this is not really required. The plant runs continuously 24/7, and accordingly, the documentation differs in both the plants. Okay, so this is why I put this slide here. Now here you see I've broken up the type of process plants into continuous plants. So you have oil and gas upstream plants from wellheads. GOSP is gas oil separation plants. CPF is central processing facility. These are oil and gas upstream basically. Okay. Before that oil goes to the refinery and all. Then you have the refinery here. Petrochemical plants are downstream of refineries where you are producing specific chemicals, petrochemicals. Captive power plants, cement plants. These are all large scale plants which are continuous plants in nature basically. Here you have either continuous or batch type. Pharma plants is there. Pharma plants are typical, basically a drug, it will have maybe 10 or 12 steps. Each and every molecule is added one by one. So to make that particular drug. So all of these are batch processes basically. Then you have small scale industries are there, specialty chemical plants is there. These are just, I'm showing overall what are the types of plants. Each and every has its own different specialty, like perfumery plant, for example, you have to be careful while final distillation is carried out of the perfume, because you have to conduct it under vacuum conditions, very low temperatures. You don't want degradation, for example. Otherwise, the perfume, if you have charring occurring, then the perfume loses its smell. It becomes a bad odor sort of, So this all has to be understood by the process engineer in each and every plant, for example. Now, project types and stages in CPI. Now, this slide I've put here to explain what are the different types of projects basically. Now, what is the cost plus free reimbursable? Maybe around 12-15 years back, I was in a project where a plant from France, which was about 40 years old, that plant was shipped to India by a particular large client. And in that plant, since it was 40 years old, the plant was shipped to India. Now, there are many equipments which may not function. So when you want to assemble the plant and run that plant, it is possible that, let's say, the X pump may not run because it's too old, for example. So in that case, that pump has to be procured new. So that's why that particular project was carried out in a cost plus fee reimbursable basis. So that the engineering firm, whatever actual man hours are booked on the project, will be reimbursed by the client, so that there is no loss occurring to the engineering firm. Now, EPCM and EPC, I will elaborate more in the next two slides. These are very important. Most projects are carried out in this fashion. And then PMC is project management consultant. So let's say a certain company has carried out a feed package engineering, front-end engineering design, what is called. So that feed package is taken by the client and floated into the market as a bid tender, invitation to bid, what is called ITB, to obtain a EPC bid from the bidders. So in that case, the consultant who has carried out the feed package may be requested to become a PMC by the client, supervising the EPC contractor engineering documentation. Now, engineering can be of many types, as can be seen here. These are the many types of engineering. Feasibility study, I will show all these in the upcoming slide. What are the differences, which documents are produced by a process engineer. Feasibility study is a DFR, basically, detailed feasibility report, which is carried out in the very early stages. And here, for example, PNID may not be even produced here. Okay. It is basically for the client to get an estimate of the cost plus minus rough order of magnitude value, so that he can then decide whether to continue with the project or not. That's why it's called feasibility study, whether it is feasible or not. Then you have pre-feed is there. BEDP is there, which is basic engineering design package. This is normally produced by the licensor. So for example, if you have an alkylation plant, let's say, the alkylation plant licensor normally is a UOP, Universal Oil Products. They are very masters in the alkylation technology. So he will give a BEDP package to the engineering consultant. So that is called a Schedule A. UOP calls it Schedule A, for example, Schedule A package. So that contains all the information using which the engineering consultant carries out further engineering, detail engineering, etc. basically. Then you have front-end engineering design. This is basically carried out by the client using an engineering consultant to establish very good accuracy of the project cost. So normally a front-end engineering design takes about 6 to 7 months. All disciplines are involved in this. Only difference between feed and detail engineering is procurement is not done. So in the feed stage, there is no procurement. No order is placed. Only the engineering is brought to a large definition so that the ITB can be floated to market by the client to get EPC bids. and then the EPC contractor will carry out the detail engineering. This detail engineering is where actually procurement is carried out and you issue documents for construction, okay, so that the actual plant can be erected. I will explain all this as we go along. Now project can be greenfield, brownfield. This also we'll elaborate in the upcoming slide. Now here's a EPC contract. So as can be seen, normally the owner, once he has the feed package in hand, he floats the ITB to the market to obtain EPC bids basically. Okay. Now the EPC contractor does a lot of pre-bid engineering, maybe 2.5 months are required for a large plant. He carries out the complete pre-bid engineering to obtain actual definitive cost of all the items. See, the EPC contractor here is placing the orders on all these other items. Please remember, he is placing the orders on equipment for the suppliers. It is a lump sum contract. So the EPC contractor suppose specifies 1,000 crores. That is the cost. The owner is going to award the contract to him. Suppose he finishes at 950 crores. 50 crores is the profit he makes. Suppose he actual project executed at 1100 crores. 100 crores is the loss to the EPC contractor. Okay. So that's why this is this has to be a little bit careful here. Process engineer has to be a little bit careful. What has been in the pre-bid stage, what has been costed, you should not accept too many changes to the design after that. So the process engineer has to be a little bit careful in that. Now, as I explained, this is the EPC contractor who is placing all the orders here. Okay, on all the contractors, including E&I contractors, that is electrical and instrumentation contractors, mechanical contractors, piping contractors. So all the document which the process engineer produces from the engineering consultant firm has to be with the mindset of an EPC contractor. That is why I am put a slide here basically. Now in EPCM, as can be seen, the owner places the orders for all these fellows. Okay. So construction contractor, other contractors, suppliers, OEMs, owner is directly purchasing all these items. EPCM contractor is there as a right-hand man of the owner who supervises the engineering, procurement and construction management. Okay, not construction management. So that is why the liability and the risk is quite less in this as compared to the EPC contract. So here, for example, EPCM contractor normally goes by the man hours. So he specifies certain man hours to the owners. To do this job, I require so much effort in man hours. And in case some gold plating is there, that can be accepted by the EPCM contractor without large liability or loss to his company. Now here we see a slide, greenfield versus brownfield. So as the name suggests, greenfield is basically you have grass vegetation which is cleared away, okay, before the plant is erected. All the equipments etc. are newly procured. Greenfield jobs are always easier to engineer than brownfield, okay. Brownfield job means, let's say you are doing something in a running plant. So in the running plant, the client wants a certain, let's say, a revamp is there. Maybe he wants to add a certain number of pumps more. Certain equipment has to be demolished and a new equipment put there. These are brownfield sort of projects. They are very difficult. They're much more difficult than greenfield. And you have many other types of documents also. Like for example, tie-in P&IDs are required, where you establish the demolition as well as new ties. Okay. A lot of times, if some pump or vessel has to be removed, maybe that pump is you have to procure new, so that engineering also will come into play. Adequacy of the existing utilities also needs to be studied while you are doing brownfield jobs. And most importantly, in a brownfield project, the process engineer has to make a site visit before he estimates the effort required, unlike a greenfield job where no site visit is required by the process engineer. Now here you see various project stages. So as I explained earlier, stages of a project. You have the alternate name of that stage. Assess stage is called mostly conceptual stage. The accuracy is plus minus 50%. You do not ever produce P&IDs in this stage. Piping and instrument diagrams are never produced here. Then you have a select stage, which is pre-feed. Accuracy is slightly improved here, as you can see. Feed year stage, normally plus minus 10 is required. So that means you do a lot of engineering, including all other disciplines also, not only process. All disciplines have to do the engineering so that the bill of material, okay, MTO, what is called material takeoff, is established to a good accuracy, so that overall you get plus minus 10% accuracy. In the feed stage, actually bids are sent to the market to get budgetary quotations so that the cost estimate can come to this range basically. And then of course detail engineering is you are actually going ahead with procurement and implementing of all the equipment, erection, etc. And operate is of course operations. Now we come to the overview of the process documents produced in each stage. This is a brief overview. So here, for example, identify or assess stage. You do not produce PNIDs. Okay, never you produce PNIDs. You produce more like a block diagram. PFD also is not produced. Evaluate or select stage, for example. Again, these are the documentation. These are all process documents here. PFD, PNID, product feedstock specification, heat and material balances, as is called, equipment list, electrical load list. Electrical equipment is also called electrical load list, which is normally started with a process engineer. And then you have the defined stage. So this is the feed stage basically. So here you see pretty much process PNIDs are almost completed here. Okay. And then execute is of course your detail engineering. So here you actually issue PNIDs issued for construction, IFC stage what is called. So there should be no holes here. All vendor information is part of this. Okay, so these are the different levels, process documents. Now we'll start with the engineering disciplines, codes and types of equipments in CPI. Here you see in the engineering. Hello.
Yes, sir, we can hear you.
See, I was interrupted in the middle. Did you know which slide? I think somebody removed me or something from the meeting. Hello.
You were
Yes,
discussing
sir.
about deliverables in different phases of project.
Yeah, so I will start again. I'll share my screen again 1 minute. Please tell me if you can see my screen. Huh?
Okay, sir.
Okay.
So,
I think the last slide. Okay. This was the documentation.
We're not
Now
seeing
this
your screen.
is the engineering
We're not seeing your
disciplines,
screen,
codes and
sir.
types of equipment in CPI. Can everybody hear me?
yes, we can hear you, but sir, the screen is not visible to us.
Why it is not visible? I have shared the screen. 1 minute. Huh? Okay, now can you see?
Yes, sir.
yes,
now
sir.
it is visible.
Yes, sir. Yes, sir.
Okay. Okay. Huh? So we'll start with the engineering disciplines, codes and types of equipment in CPI. So these are the engineering disciplines involved in a typical engineering consultancy. Here you have process, mechanical, instrumentation, piping, electrical, civil, technical safety. And you also have large consultancies will also have a materials group. Material engineers are there who specify the corrosion and materials properties, especially nowadays with the vast range of chemicals, etc. So materials engineers are also very important here. And then these are the support disciplines basically. Okay. So this is a typical engineering consultancy composition. Now we'll go to the next slide. These are the various codes typically used in projects. These are typically used in India. These are the standards used. However, it depends on the country. Like if for example, in Europe, you have many other standards, like DIN standard is there in, DIN standard here is mostly used in Europe, this one. Okay. Then this DNV standard also is used in Europe. Then in Russia, if you go, they have a GOST standard. So each country has their own standards also. Many of these standards are mandatory. Like for example, this standard, if you are producing a petrochemical or a refinery, then these standards are mandatory. LPG storages, LNG storages, all of them come under the PESO. IBR is mandatory in India for steam and steam networks. Okay, so it depends. These are the many standards. OISD is also mandatory for certain industries, oil and safety oil industry safety directorate. Now, just a few major equipments I'm going to mention here. We don't have, it's a brief introduction today, but these are all the types of equipments, for example, which you will see in chemical industry. Pumps are very predominant. Compressors will be there. Then you will have separators will be there. Fire heaters, depending on the process. Heat exchangers are very common. Utilities. This is another very big area where the engineer needs to understand. A firefighting system normally is done by the technical safety. I've just listed it here. These systems are engineered by the process engineer. Okay, we'll briefly touch upon these as we go along. Now pumps. Just a few slides I've added on the pumps. So the pumps are, for example, dynamic category here, you see, centrifugal type. Then you have the positive displacement type here, which are reciprocating, piston, diaphragm, rotary. Okay, so many types of pumps are there. Each and every one has its own application area, own limitations, etc. Then coverage, as I mentioned, these are the coverage areas of the different types of pumps. So for example, here you see solid lines, use the left coordinate. So these are the solid lines. So centrifugal pumps are always measured in head. Okay, centrifugal pumps always in head, MLC, meters of liquid column, and the capacity is there. And where the broken lines is there is the right coordinate, pressure scale. So if you see the broken lines are gear pumps, these are PD pumps basically, positive displacement pumps. So always the discharge pressure is specified here, okay, for a PD pump, flow and discharge pressure. Here you can see the axial flow pumps are very large capacity type with a low head. As you can see, the head is quite low. Agricultural sort of pumps, these are axial pumps. Then we see the dynamic versus positive displacement pumps. You can see the parameter versus the overview of the differences basically. So this is the characteristic curve. So PD pump always, it is a straight line, vertical line. So flow will be same. The discharge pressure, it will keep on pumping, pushing liquid if the valve is closed on the discharge until something breaks. So normally you have a safety relief valve on a PD pump discharge always for protection. A centrifugal pump is, that's why, limiting on the head. Okay, the self-limiting, that's why, on the head part. So this is an overview of the PD versus dynamic as can be seen. Now here we see process parameters to be specified for centrifugal pump. So these are the process parameters which are usually specified. API is a very robust pump. API 610 is followed for centrifugal pumps and other APIs for other reciprocal pumps. They are very costly, but maintenance is less. ANSI pumps are for small chemical pumping. HI is Hydraulic Institute, and manufacturer code can also be applicable. For example, if you have a HDP pump or a PP pump, plastic pumps, you follow manufacturer code. So all these are the parameters that a process engineer specifies. So centrifugal pump, for example, suction pressure, this is how you calculate. NPSHA is net positive suction head. This is how you calculate. Differential pressure, always in this fashion. Hydraulic power in kilowatt, this is the formula used. And pump BKW, brake KW, this is the formula used. The pump efficiency comes into play. Then you have a PD pump, for example. These are the various types of PD pumps. As can be seen, a vast variety is there. Okay, each has its own application areas and advantages, disadvantages, which I will not go into in this webinar. But many types are there. A lot of elaboration of this has been done by me in the book, as well as in my coaching class also, which I will come to. Now again, the coverage, same coverage I presented here, where a lot of PD pumps are there, gear pumps are there, many other types of PD pumps are there. Metering plunger is there here, diaphragm is there, screw pump is there here. Okay. Again, process data to be specified for PD pump, similar to the centrifugal. Then we come to the calculations for PD pump. So these are the, again remember, PD pump also has an NPSHA requirement, okay? Only the difference between PD and centrifugal is suction pressure, you add the acceleration head, because this is pulsating flow. So if you have a metering pump, it is pulsating flow, so acceleration head comes into play. Otherwise, the other formula is pretty much similar. Now compressors we'll cover here. So there are many types of compressors available, as can be seen in this chart. You have dynamic on the left side. The thermal jet are the ejectors, basically steam ejectors, for example. Or you can have the eductors. So when I say thermal, that will come to steam jet ejectors. Then you have the PD positive displacement type. So recip is there, piston diaphragm. This diaphragm is very important nowadays, that this hydrogen is taking so much precedence. So for example, in a fueling station, vehicle fueling station, where hydrogen is used as a gas, normally the pressures are very high. You have 350 bars because it's a very light gas. So you have to pressurize more so that you can have more storage in kgs in that particular small cylinder in the vehicle. So in Europe and all, they are using 700 bars also. In India, so far 700 I have not come across, but 350 has started basically. That's where these diaphragm compressors come into play. And then your rotary here you have, for example, screw, lobe, liquid ring, what is called LRVP, liquid ring vacuum pump is called. So these are the different types of compressors. Some more compressors are also there, like scroll compressor. I have not listed it here. Then the brief comparison between centrifugal and PD compressors. So parameters there here, as you can see, on a brief comparison, many more parameters are there. So centrifugal compressor here you can see, non-lubricated type, and positive displacement can be lubricated or non-lubricated both. Okay, one has to accordingly be careful. For example, screw compressor is normally used for air service. So one has to be careful. If you use a lubricated compressor, you'll have oil carryover in the instrument air, which is not good. So you have to be careful with the filters and all on the discharge. Or you can have non-lubricated screw compressor, which is called oil-free screw compressor. This is important, the reliability. As can be seen, centrifugal is quite reliable here, 99.5%. Recip and all reliability is quite low here. Screw compressors are also quite reliable. So this this reliability is very important in critical plants. So a RAM study is conducted, reliability, availability, maintainability, in which a process engineer also participates. Now here we see a brief comparison between various major compressor types. So recip compressor, as one can see, these are the salient features. Lower reliability, available in smaller capacities, can have very high discharge pressures, need proper supported piping due to the high pulsation. This is very important. So recip compressor, always on the suction side, a pulsation study is done for large recip compressors, because the piping supporting has to be taken care properly. The foundations are required to be strong because of this nature of the pulsations. Centrifugal compressors are constant head machines. Then similar to the pumps, basically centrifugal pumps can have very high capacities. They are not economical at low capacities. Okay, so you need to have centrifugal compressors always at high capacities. Then the surge limitation at turn down. So this is the important thing for centrifugal. You cannot go very low on turn down. The compressor starts surging. And they have a very high reliability and low maintenance. And screw compressors are wet or dry screw. Okay. Again, the coverage chart I've given here, as can be seen. So here you see the centrifugal is on the right side here, large capacities, and the recip compressors on the smaller capacity, left-hand side, but for very large discharge pressures. So discharge pressures can be quite high here. And then you have the screw compressors in the central here. Eggshell fans are here in the low pressure range. Capacities can be small to large. Process inputs for compressors. Process engineer needs to provide following inputs basically. In is a process data sheet basically. The process data sheet will contain all these inputs as can be seen. Now heat exchangers, just briefly I am covering this. It's a vast topic. In my coaching class I have taken about 7.5 hours for all the videos on heat exchangers. Here we will quickly run through. So many types of heat exchangers are there as can be seen. Here also you have heat exchangers, many types. Each has its own application area. 80-85% are the shell and tube types. Okay, this is very important type. And you have very good softwares like, for example, Aspen has EDR, which was earlier called STFS. Then there is STRI, Heat Transfer Research Institute, which is predominantly used nowadays for shell and tube heat exchanger design. And the process engineer carries out the thermal optimization of the exchangers, thermal design what is called. But there are, as I explained, many types are there. Air-cooled heat exchangers are also quite predominant in the refinery and petrochemical plants. Okay, we'll just cover the shell and tubes 2-3 slides here. So over 85% heat exchangers are shell and tube types usually, can be designed for almost any duty with a wide range of temperatures, pressures. Material of constructions can be quite exotic, varied, common, many types are there. Many suppliers are there, okay, who are familiar with the TEMA standards, ASME Section 8 Division 1 and TEMA standards, and hence choosing the supplier is not an issue, unlike some of the other specialized exchangers. And design methods and mechanical codes have been established many years basically. Then now we come to utilities. This is very important. Any chemical plant, whatever you have, any chemical plant will always require utilities. Okay, refinery may contain all of these, for example, but let's say small scale industry may have a few of them. Okay, not all of them. So we will cover the utilities. It's very important for the engineer to understand each and every type of utility. And one should be familiar with this so that one can use this knowledge in their field in a proper fashion. Okay, I have given a lot of advice in my further slide for the freshers and the youngsters. I hope they abide by that. We'll come to that slide separately. Okay, we'll start with the plant air, a brief slide on this. So these are the equipments used here: filters, compressors, wet air receiver, also called plant air receiver, from where plant air is taken. Plant air is wet air basically, okay? It is used for cleaning purposes in utility stations. Then you have the air dryer. Air dryer can be of many types. There are about 6 types of air dryers, depending on the capacity and the outlet dryness of the air required. Then you have a dryer receiver, this one, which is also called instrument air receiver. So this is normally sized for 15 minutes between certain pressure ranges, so that in case of any upset condition, the operator can go and shut down the plant safely within that 15 minutes. So from here you take instrument air. Then you have water systems. Water systems can be many in a large plant. This is just a brief schematic I've given for your understanding. So for example, raw water comes here. Again, raw water can come from many sources. You can have desalination plants. You can have your let's say in Maharashtra you have MIDC, for example. Gujarat you have GIDC, who supplies the raw water. So raw water tank is there. A fire water directly taken here. This is fire water. Then it goes to the fire water system. Raw water then can be used in cooling tower as a makeup. You can have utility stations. You can treat it, remove the algae, make it potable water, which is used for safety showers, drinking purposes. Or you can take as a tapping for a DM water unit, demineralization, softening unit, which produces DM water, which is used in the, let's say in the actual process, you may use it in a reactor, for example, or you can use it in boilers, etc. So this is a water system. This is a steam condensate network. This particular diagram is for a large refinery, for example, where you have many web pressure levels. Here you see 42 kg per cm square pressure level, 600 psig network is there. So the boiler, this is the boiler fellow here sitting here. The boiler is producing steam which comes in here, pressure controlling the boiler. And from here you are letting it down from turbines etc. to another level, 150 psig steam header. Okay, you can have a desuperator also here. PRDS is called, pressure reducing and desuperating station, PRDS. And from 150 again you have consumers here. So using the consumers like this heat exchanger is there, and then the condensate comes out. You can have turbines here, and then this is the low pressure header here, 3.5 kg, 50 psig steam header, and the condensate is recycled back to the flash drum, to the deaerator, where the CO2 and oxygen are removed, and then the boiler feed water pumps it back to the boiler. So this is a typical boiler, large petrochemical refinery plant, steam condensate network system. Then typical hot oil system. Hot oil is a thermic fluid which is used in place of steam. For example, in applications where your process temperature is quite high, let's say you want 250 degrees centigrade as the process heating. Obviously, you cannot use steam because steam pressure becomes very, very high at that temperature. So all the systems will have to be designed for that particular pressure, which becomes slightly uneconomical. So that is why if your process temperature is 250, it becomes very economical to use a thermic fluid system like this hot oil system. So there are many types of thermic fluids available depending on your temperatures, and they can withstand very high temperatures. So basically you have pumps, expansion tank, pumps. This is the main fire heater. You have the users here, and then the hot oil comes back to the expansion cum deaeration tank. This is called expansion cum deaeration tank, and then from here again pumped through the circuit. So this is a typical hot oil system. Now nitrogen system again, filter is there, compressors are there, plant air buffer is there, nitrogen generation unit is there. It can be PSA or membrane or cryogenic. Three types are there. Cryogenic is economical at large capacities. Otherwise, you have a PSA or membrane. And if your oxygen you need very less, at the outlet of the engine, a deoxo unit is put, where you input hydrogen or ammonia, which reacts. The hydrogen reacts with the oxygen to make water, and thus the oxygen in the final nitrogen can be reduced to very less levels, ppb levels basically. And then final nitrogen buffer is there before it goes to users. This is a nitrogen system. You can also have a cryogenic liquid nitrogen backup storage here. So if the nitrogen is very critical, in case this system fails, a liquid nitrogen backup system of let's say 10 meter cube can be here through the air fin vaporizer and put the nitrogen into this header. Then you have effluent systems. These are the ETP basically, effluent treatment plant. So normally this is the whole thing is part of the ETP, effluent treatment plant. Again, it depends on the particular chemical, what are the effluents produced. So it is not one size fits all. It has to be engineered. So a treatability study has to be done for that particular effluent coming out from that particular plant, and then the configuration of this ETP is finalized. Okay. So here typically here you see this is a generic diagram I have drawn here. So here you have the first flush of rainfall. First 15 minutes of rainfall is taken into this pit basically before it is allowed to go to stormwater drain, so that all the floor is washed because you may have spillages of chemicals on the floor. You add pH adjustment, coagulant, flocculant, process effluents. Then you have the basically this is the main ETP plant, primary treatment, secondary treatment, which is biological reactors here, and then tertiary treatment, which is activated carbon filters. So you have clarification.
Hello, sir.
Hello. Yes.
Hello, sir. Good evening, sir.
Yeah, good evening.
Sir, Himanshu this side from Nagpur.
Can you please wait till the end? I will finish my presentation.
Sir, actually, I had one doubt, sir.
Himanshu, you are. I will request you
Hello?
to keep your mute. Please keep on mute yourself, because we are taking the questions at the end of the presentation, if time permit, because sir has limited time, given us a limited time. So please keep
Okay.
on yourself mute, and we will discuss it on later base. Okay.
Okay, sir. I'm sorry, really sorry for the interruption, sir.
So I'll continue with
sir.
this. So
Yes,
I'll
Mr.
continue
Please
with
continue.
this. Hello, can you all hear me?
Yes, sir.
Can you see the
Yes, sir.
slide?
Yes, yes.
Okay, so let's continue. So this is the typical ETP configuration here. Primary treatment is clarification, flocculation, etc. Secondary is biological treatment, where bacteria is cultivated, which eats away all the effluents. And tertiary is activated carbon filter for final polishing. Now, one important thing is, see here you see, there are certain effluents which are clean effluents, which need not go through this system basically, okay? So these are DM unit effluent. Let's say you have a demineralization unit which is using the conventional ion exchange resins. So those effluents are normally quite clean after neutralization to 7 pH. They have a little bit of TDS, total dissolved solid. So these can directly be taken to this guard pond at outlet of this main ETP plant. Cooling tower blowdown, similarly, boiler blowdown. These are taken to the guard pond. This guard pond is kept so that in case you have any upsets here, you do not pass this effluent outside of your complex basically, okay? That's why it's called a guard pond. Typically 1 day storage. And from here now you have many options here. You can put up ultrafiltration, reverse osmosis and take the permeate from the RO, use this water back. So this is called a ZLD plant, okay? Zero liquid discharge. So even the brine from the RO is taken to a solar evaporation pond. So that is called a ZLD, zero liquid discharge plant, okay? So nowadays the pollution boards are getting very strict. They go with this concept, ZLD, for large industries. So the industry basically reuses the water into gardening, cooling tower makeup, and the final brine is taken to a solar evaporation pond. Or you can also have the brine taken out to a central effluent treatment plant, what is called CETP. For example, in India, in Vapi, they have a central effluent treatment plant called CETP, where you are allowed to put clean effluents basically. So this brine is nothing but water with a high TDS that can be taken there. Now, typical flare system, this is a safety system. So wherever relief valves and rupture discs are there, this is the typical system. Flare headers are there, flare KOD is there, knockout drum, and finally the flare stack. This is a typical safety system. It is a very important system for large refineries, petrochemical plants, so that you do not put into atmosphere any unburned hydrocarbons, etc., which can cause flammable clouds in the area, which is very dangerous. So that's why the flare system is a safety system basically. Now refrigeration schematic. For refrigeration, basically the conventional refrigeration system I am showing here. There are absorption refrigeration types also. So here basically you see the evaporator is where the main refrigeration occurs. So here your let's say chilled water comes in, return, supply chilled water and lower temperature goes out. You have the refrigerant evaporating, gas going to the suction of the compressor. This is the low pressure side here. Compressor discharge going to the high pressure side here. This is the high pressure discharge of the compressor. Condenser is there. You can have air cooled or you can have a water cooled condenser. And under high pressure, this is the gas is refrigerant is made liquid. Two phase comes here, and the liquid in the expansion device. It's a JT valve basically, Joule-Thomson valve, where pressure is let down. It basically evaporates. Here you have two phase also. This is liquid coming into the JT valve after the condenser. After the JT valve pressure let down becomes two-phase before it goes to the evaporator, where the evaporation of refrigerant occurs. So this is a conventional refrigeration system basically. Here you have a typical chill water system. As I explained, this is the evaporator where that chill water is produced. This is the chill water circuit here. Okay, chill water circuit going to the plant for the various loads. AHU is the air handling unit, for example. Okay, then the FCU is a fan cooled unit. Then this is the water side for the condenser side. So this is a typical chill water system in the chemical process industry. Here you have a heavy fuel oil. Large refineries, petrochemical plants where they have many fired heaters. You use heavy fuel oil, for example, HFO. So this is a typical HFO system. So this is a strainer HFO pressurizing pump. You may use a triple screw pump, gear pump. This is a heater is kept to maintain the viscosity of the heavy furnace oil. The viscosity needs to be maintained at around less than 25 centistokes. Otherwise, the burner will not be able to combust the furnace oil properly. Atomization will not be possible to do properly. So that's why this heater is put here. And you have a recycle coming back here. So this entire header is kept pressurized condition. So whenever the fired heater starts, the network is pressurized. You can start the burners at that fired heater. Then typical fuel gas system. So here you have a vessel here. Natural gas, butane or propane is coming. This is the tail gas from process units, which is additional gas. You can use it for combustion in the fuel gas to burners. Earlier slide was of the furnace oil. This is the fuel gas to similar fired heaters. Okay. So this is the KOD knockout drum. You keep heated here, condensate. This line also is steam traced. Okay. This line going to the burners is steam traced. Steam or electrical traced, so that you don't have any condensation occurring. You don't want liquid to go to the fuel gas in part of the fuel gas to the burners, because that will cause fireballs inside the fire heater. So this is a typical fuel gas system. Then you have a cooling water circuit here. This is a backup water. Cooling tower is there. You have the pump, circulation pump, users. This is atmospheric. This is vented to atmosphere. So it is atmospheric gravity flow coming back here. That's the gravity flow shown here. Okay. And then it comes mainly to the cooling tower. Roughly around 4% of this circulating water is passed through the AVGF, what is called. You can also have AVGF basically doesn't need any operating cost. OPEX is not there. You can also install a filter, pressure sand filter on the discharge of the pump and take the water back to the cooling tower. But then your pumping energy is wasted in that PSF. So that's why people nowadays prefer the auto valveless gravity filter. This is a typical cooling water circuit. A slight purge is kept of this blowdown depending on the cycles of concentration back to the ATP. Now process engineering documents will quickly cover. So these are the overall process engineering documentation produced in any project. Again, it depends on the scope of the project plus what stage you are producing the documents. As I explained, pre-feed, feed, detail engineering. Okay. So that all depends. Like for example, operation maintenance manual is only a detail engineering documentation. You do not produce this in a feed stage. Okay. So it depends on the document. According to that, the documents are produced. Now we go to the next slide. So this is a BDEP documentation process. Now basic engineering design package is usually produced by the process licensors. As I explained, for example, if you have an alkylation plant, UOP is the licensor, so he will supply a BDEP package to the main engineering contractor. So in the the process licensor will supply this, since they are providing the performance guarantee. The process licensor is taking the guarantee, so he gives the basic design in his package. The engineering company further carries out either feed engineering, so that the ITB can be floated to market to get EPCM or EPC bids, and residual process engineering or detail engineering. So depending on what the client requires, the engineering company can do feed or go straight on to the detail engineering. And the BDEP normally contains these documents. So as can be seen, preliminary equipment list is there. This may not contain the offsite and utilities equipments, which have to be added by the detail engineering contractor or the feed engineer. And similarly, critical equipment data sheet like reactors, etc., that he has to provide basically. Now feed documentation. So this is the typical feed documentation. So here you can see the operating and maintenance manual is not there, which I explained is part of detail engineering. Okay. And then the process engineer also participates in many safety studies, which are listed here basically. So this is the typical documentation produced in the feed stage by a process engineer. Here if you see surge analysis, ramp study, etc. also there as applicable to the project. Now here you see detail engineering. So during detail engineering, the process engineer produces following additional documentation over and above those listed in the feed documentation. So P&ID is a IFC, okay, issued for construction and as built. Alarm and trip summary is produced in detail engineering. DCS graphics are produced, okay, distributed control system graphics are produced so that the DCS can be accordingly made by the supplier. Operation maintenance manual is there. Following activities are part of the so vendor drawing review. See, as I explained, in detail engineering, the procurement is done. So the vendor drawing documents you'll only receive as part of detail engineering. So VDR is a very big activity which is there in detail engineering. Okay, it occupies a lot of time. Huh? Isometric checks are there. Final pump head verification after the isometrics are available. Model review. Participation in the factory acceptance test of the DCS, etc. PLC, DCS. Site visits for punch listing. These are all part of detail engineering documentation. Okay. And finally, if the commissioning and all is there, then you participate in that also. Commissioning is the cream of a process engineer's job, huh? Because you actually see the equipments come alive, what you have engineered. So it is a very good stage of a process engineer in a project. Now, I've given today's webinar is very brief. I've given a 2.5 hour webinar. You can access it on this YouTube, this particular. It's called Introduction and Keynotes on Chemical Process Engineering. It's a free webinar available on YouTube basically. Then this is important. I want to advise to the youngsters, freshers who are there participating in today's interview. We'll spend 2 minutes on this. See, all of you are in the formative years of your career. Now, please concentrate on knowledge enhancement. Okay, that is very important. This will help you 10 years down the line. You guys will be able to demand your salary. Okay, this is very important. Don't get satisfied that, okay, you are getting some 1 lakh rupees per month. So fine, that's fine. I'm very comfortable. No, your emphasis should be on knowledge enhancement. Put in your best effort wherever you go, please. This is very important. Okay. Go after excellence. Excellence and success will follow. I hope you guys remember the 3 Idiots movie. In that, this was a very important part of that 3 Idiots movie. In whatever you do, success will follow automatically. While in gaining knowledge, this is very important. Okay. I remember in '86 when I started my career, my first job. There was no mobile phones, internet was not there. My first job was in a textile company and I had to struggle for more than 6 months learning the background of textiles, which is different than chemical. Okay, it was a POI manufacturing yarn, partially oriented yarn. I went to the library also, this was in USA. I went to library, I could hardly find one book on it. So nowadays this internet is very good. You guys can gain a lot of knowledge. So it's up to you what you do, okay? This is also very important. Concentrate on learning. Please do not gossip or play politics in the company that employs you. Okay? Your emphasis should be on learning because these are your formative years. Most important, this is very important. Keep a positive attitude at all times. Remember that the companies hire you so that you can benefit them to be more successful. Hence, always think how you can help your company to grow further. This is very important. I hope you guys remember this advice, and that's all I can offer you other than what my knowledge is. Now here I'll just briefly spend 2 minutes on MIHIR's Handbook of Chemical Process Engineering. It is available at this website. It is available in these many versions, as you can see. Android app also is there. In fact, I have that on my phone also. It's quite useful. The student version we have introduced recently. So you can visit this website. On the same website, I have started my advanced course also on chemical process engineering, which are pre-recorded videos of quite intensive knowledge on each and every topic. These are the topics basically. Each and every part of chemical engineering I've tried to cover here, and extensive knowledge I've tried to impart on this. This is the page 1 of the topics of the advanced scope. This is the page 2. As can be seen, all these utilities has its own webinar, okay, with a lot of knowledge enhancement there. Plus, a lot of other things are there which a chemical engineer requires in his career, okay, including pre-commissioning, commissioning. Then you have cost estimation and analysis. This is very much required in the detailed feasibility stage of the project, DFR, what is called. Control and automation, all these things are. PNID has a separate webinar, maybe I think about 3 hours it is lasting. And then in each and every webinar, I try to cover all these things which are very relevant to the process engineer. Fundamentals, application areas, codes and standards, process schematics, inputs required, process calculations with examples, datasheet preparation, control methods, layout related location, procurement strategy, which is important. So I sincerely request those who are really interested can also avail of this knowledge quotient. Okay, I'm at the end of my webinar now. I'll go back to the teams, and I would like to ask Omkar. I'm going to stop sharing now, so you can take over, please.
Yes, sir.
Okay. Thank you. Yes, am I audible to everyone?
Yes. Yes.
So thank you everyone. Good evening everyone. And so I would like to thank Mr. MIHIR Patel sir on the behalf of Beginnings Organization that he has explained us all about the chemical engineering knowledges. He shared all about his experience also. So on behalf of our Beginnings Organization, I extend a warm welcome and gratitude to them, to sir. Okay, and also our chief guest, MIHIR Patel sir is our chief guest and speaker. So he has very busy schedule but he came into the web to came give us a webinar. Okay, so that is very thankful from our side, sir. Okay, then I must thank the organizing team also and volunteers who are working hard for the past few days to arranging this webinar on a successful basis. So I congratulate all the participants for their activities, active participation. I would like to know you all that we will take all your questions through email. So please do write your all the questions as me sir is on. I mean he is in still in Oman, so he will leave us shortly. He's not able to take all the questions. So you please write all your questions, all your queries through mails. We will definitely answer them in a short period. Okay. So thank you everyone. Yes, Omkar, if you have any other suggestions or if you have any word to say, please continue.
Okay, so thank you everyone. Thank you, Mir sir. If anyone want to buy the book, I will share the link for the same on the mail. You can reach us on the mail info@beginnings.org. We will revert on the same. Okay, thank you, Mir sir. Thank you for your valuable guidance and time.
Then most welcome everybody. And I sincerely hope you guys take my advice, what that one slide I had put, and accordingly proceed in your life. Huh? Thank you and all the best to all of you all. Take care. Bye.
Thank you, sir.
Hello, sir.